As we wrap up equilibrium, we're connecting KSP, or our equilibrium constant, to precipitation. With KSP, we're talking about ionic compounds that we define as slightly soluble. In general, or up until these past few videos, we said that those are things that do precipitate, and they do, meaning that very little of it can dissolve, so most of the time they turn into a solid. But if we have, as we've seen, very, very small amounts of them, we could have a very small amount of that ion dissolved in water. We can use our K value, we can connect it to Q and think about, in different solutions, how much of those ions are needed before a precipitate forms. When we do it in the lab, we're normally talking about molarities large enough, even 0.1 molar and 0.1 molar of this are talking about values are going to give us things enough that a precipitate will form. When we're talking much smaller, we're thinking about, are we above or below the molar solubility for this? So the way we do this is thinking about what has to happen to get to that equilibrium. When we have very, 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 very low concentrations of something, when we plug those into our values, our initial values there, and solve for them, they would be our Qs. If that Q is tiny, then that means the amount of those ions is so small, it's not yet at equilibrium, or those can stay dissolved. It would be an unsaturated solution, and even if that's something we normally would define as insoluble, there's not enough of it there to precipitate. When Q equals KSP, the system is at equilibrium. That's right when we're at that maximum amount that can dissolve. We're really not going to see this in these sorts of problems because at that point, we do have to have some solid and some ions. So, but that's right at that moment or right at the maximum amount that can dissolve. But if I have calculated my amounts and I see that my molarities of my cation and anion are higher than what they should be at equilibrium, my Q is higher than my KSP, it's not at equilibrium, I've put in too much. We would say, maybe a phrase that's commonly used is that it's super saturated, or I have more there than could be in a saturated solution. That's when it forms, and it doesn't stay dissolved, it forms a precipitate. That's what happens in most supersaturated solutions. This problem down here has some good tricks to it that is going to be important to watch, because not only do I do a K calculation there, this phrase, which will come up in solutions, probably in acid base, and obviously right here, is helping us to recognize that although I'm given molarities of my chemicals here, if I mix two solutions, I am increasing the volume of my final solution. So the given molarities aren't exactly the molarities that I can plug in. So we have to do a little bit of extra math, or recognizing that mixing that solution one, the cerium nitrate, with solution two, the potassium iodate, we actually kind of water down all of those ions in the process. Another thing to mention, and that's kind of the math for it here, is if we have different chemicals kind of floating around in a solution, a lot of times, we do what we call a qualitative analysis, where I've got multiple ions in a solution. What we would do was we could think about the KSP for all those different things and recognize which ion is going to precipitate first. The thing with the lowest K is the thing that can dissolve the least. So I can, one at a time, precipitate maybe just lead, or precipitate just silver, or just a specific ion, but not others, by adding a certain anion with it, or adding a certain amount of an anion, where one would dissolve and another would not. So that's a good qualitative way that we use KSP values, or you can be asked about them in a multiple choice. Which of these will precipitate first, by looking at, as I add a certain chemical, which needs less before a precipitate